where we ended, what was it, Tuesday? We looked at ionic bonds. And we said that when we're looking at ionic bonds, what's happening, or the characteristic between these, is that we've got a metal and a nonmetal. And if we look at the charges of our metals and nonmetals, so if we go all the way back to what we talked about, well, actually I think we talked about that also on Tuesday, our metals typically carried what charge? Positive, and our nonmetals typically carried negative. So based on that, if we put them together into a bond, okay, we would still expect that big difference in charges, or the electron sharing. So what ends up happening when we describe the bonding in an ionic bond is a transfer of electrons. I can't say I'm a fan of that terminology, but it's the terminology your book uses, and it's the terminology that will show up on exams. Okay, so if we're looking at an ionic bond, it's a transfer of electrons from one atom to the other. So if we look at the bond, actually we'll come back to that. In general, I'm trying to decide what type of bond you have. The ionic bond is most typically found by looking for a metal. If you see a metal present, you have an ionic bond, at least as far as this class goes. Right? So that means, what is that, 90% of the periodic table is metals. So if you see any one of those symbols show up, you're looking at an ionic bond. Okay? Where we officially ended was looking at the ionic radii. So if we take a sodium atom and a chlorine atom, and we bring them close to each other, what we're trying to determine is what happens to those individual atoms in the process of forming this bond. Okay, and what we looked at was the electron configurations. So what was our electron configuration for the sodium atom? So to determine that, what will we do? What's that? So we could go through and do the whole configuration. I kind of want to cheat because I don't want to write it all out. So we'll look for the noble gas in the row above it. So sodium is in row 3, so we'll look for the noble gas in row 2, which is neon. Put that in brackets saying for sodium, it's the same configuration as for neon, and what? We now move to the next energy level, which is our third energy level, because sodium is in our third row. Okay, sodium is located in that first 2 columns. That first 2 columns is known as the S block, so we're looking at the 3s electrons. Which column is it in? The first one, 3s1. All right, if we were going to go through and do this for the chlorine atom, what do we get for the chlorine atom? That was good. Let me try that again. We've got our neon being in the noble gas immediately above the previous row. We then drop down to the lower energy level. Chlorine's in the P block, but we have to get to the P block first. What do we have to pass through to get to the P block? The S block. So we have our 3s2. Then we can move into our P block. And chlorine is in which column? Fifth. So we have 3p5. Make sense? What happens when we go through and bring these atoms near each other? Okay, well, we start to make an ionic bond. And in the process of an ionic bond, we exchange the electrons between these, or we transfer electrons. The sodium atom wants to become what charge? +1. First column +1. So to become +1, what does it do? It transfers its 1 valence electron to the chlorine atom. So what happens to the electron configuration for our sodium? It then drops down to just like neon. What happens to the chlorine atom? It's gained 1 extra electron. So if we actually wrote it out, we could say 3s2, 3p5, or 3p6, or we could say that's the configuration for argon, right? So the next question that you could run into is what's going on with the radii? Okay, so what happened to the size of each of these atoms when we went through? So what happened to sodium? How do you know it got smaller? It lost an electron. So that makes sense for it to get smaller. We removed a high energy electron, which means an electron further away from the nucleus, and we dropped down to our neon. So if we looked at our trends for a radii, sodium versus neon, which one's smaller? Neon, because it's in a higher energy level, or sorry, a higher row. Okay? So we would expect the size of our cation to shrink because it has less electrons. Right? Because we're moving between a different energy level. Make sense? So we would expect this guy to get smaller. What happens to the chlorine? Okay. Yeah, it gets larger, but now we run into an interesting question. Why? We looked at our atomic radii explanations. As we moved from chlorine to argon, what happened to the atomic radius? It got smaller. We're moving from the electron configuration of chlorine to the electron configuration for argon, and yet you're telling me it gets bigger. Why? It has to do with the nucleus. We're seeing a different change. When we moved from our atomic radii, chlorine to argon, what happened? It got smaller. Okay, we added an electron to it. Why did it get smaller? What else changed as we moved from the chlorine atom to the argon atom? The nucleus changed. The nucleus became more positive. We had to add an extra proton to it. When we're looking at our ionic radii, as I move from the chlorine atom to the chloride anion, did I change the nucleus? No, it's still chlorine. It has the same positive charge. But now what's happened? I've added an extra electron to the outside of that. That positive charge of our nucleus was already holding the electrons as tight as it could. We now add an extra electron into it. The charge is now imbalanced, and it can't hold that electron as tightly. So what happens to that extra electron? Floats out just a little bit further away. So when we look at our ionic radii, we see a slight change in our trends, and that's just because of how we're putting our electrons in and what changes are occurring. In our atomic radii, our trends are based upon changing both the electron count, or our electron energy levels, and the number of protons. When we're looking at our ionic radii, we aren't changing the number of protons. It's the same atom. All we're doing is changing the electron configuration around it. Okay? So sure enough, when we go through and take a look at actual images, our cation shrinks down in size. That one hopefully makes sense. Okay, that one's, to me at least, is a little bit easier. We took an electron from a high energy state and we got rid of it. Okay, we should shrink down. Okay. The one going the other direction seems a bit counterintuitive based off of our atomic principles, but we have to realize we aren't changing the nucleus either. Okay? Questions about that? So I could go through and say what happens to the ionic radius, or the radius of a chlorine atom as it becomes a chloride atom. What happens to its radius? Well, it gets bigger. What happens to the radius for a sodium atom as it goes to sodium ion? It gets smaller. I can get really tricky. What happens to the sodium atom when it goes to negative sodium? So a sodium anion. Okay, why is that one tricky? If I go from a sodium atom to a sodium anion, what does anion mean? Negatively charged. It means it gained an electron. What happens when our atoms gain an electron? They get bigger. Okay? Why is that a weird question to ask? Does sodium become negative? No. Okay? So it's outside our realm of what we're talking about, but it still addresses, do you understand what's happening in each of those electron transfer processes? Okay? Questions? Yes. Okay. The nucleus is getting more positive. Focus more on the more positive than bigger. Okay. Okay. Covalent bonds. So when we look at a covalent bond, what's our big signifier? Nonmetals. I would argue we could still go off of our metal system, because right now we've talked only about two bonds. It's either ionic or covalent. If you look at an individual structure and there's no metals in it, what does that mean the bond is? Covalent. We don't have a choice. Okay? So in our covalent bonds, we actually see a sharing of electrons. There's no direct transfer of electrons. So we don't see, ions pop up. So if we take the situation up here with nitrogen and nitrogen, they will equally share their electrons. Okay? Do we have a quantification that we could look back to and say, yeah, they should equally share their electrons? Said another way, is there a value that expresses the ability of an individual atom to hold bonding electrons? The electronegativity. Okay? If we look at a covalent bond, particularly for this case, our nitrogen-nitrogen, the electronegativity of nitrogen 1, anybody know what the number is? Good. Let's call it 3.1. What's the electronegativity of nitrogen number 2? 3.1. Still nitrogen. Has the same properties. Which means when I go through to put them into a bond, what happens to the electrons being shared between them? They're being equally pulled both directions, so we have to share those electrons. If we shift back to our ionic bond, the electronegativity of sodium is something like 1.7. Still waiting for someone to call me out and tell me I'm wrong on those numbers. Okay, thanks. It's close enough. Chlorine, electronegativity is something like 2.7. When we look at the difference in electronegativity there, there's a large difference. The chlorine atom is really pulling on those electrons so hard that it takes them entirely away from the sodium. So we can look at a difference in electronegativity to predict what type of bond we have as well. It's the issue with that. How many of you have memorized the electronegativities? Nobody. Okay, let's include me in that count. How many people have memorized the electronegativities? Nobody's going to go through and memorize them. What we might pick up are the general trends. Right? And so the things that we'll remember are when we're looking at an ionic bond, it's a metal and a nonmetal. The difference in electronegativity there is massive. Right? When we look at a covalent bond, we're looking at nonmetal to nonmetal, We're all now in the upper right-hand corner. And when we bond any of those elements to each other, the difference in electronegativity is now much, much smaller. Okay? That smaller difference is what puts us into that covalent category as opposed to the ionic category. Okay? And we'll look at that difference as well. What happens with the bond length in our covalent bond? Okay, so there's a couple things we can look at. We bring two atoms near each other. Eventually, what starts to happen? It's the first thing that interacts.
Electrons.
The electrons. Okay, if the electrons just see each other and that's it, what do we likely expect to happen? What happens when an electron gets near an electron? Repels. Whoop, atoms never interact. In a covalent bond, what are we saying though? Those atoms are connected to each other. So what happens? We bring our atoms close to each other and the electrons from one atom starts to see the nucleus of the other atom. So it starts to drift over to the other atom. As it drifts over, what happens? We now start to draw those atoms a little bit tighter to each other. So in a covalent bond, the bond distance is a little bit smaller than the radii because you're taking the electrons from one atom and you're sharing them with the electrons from another atom. It has to get a little bit smaller. Otherwise, they can't be sharing. Kind of makes sense? Okay, so we could go through and take a look at our radii over here. We're looking at a slight difference in our bond length. That's all this figure is trying to show. Questions about that? Okay. Next part, bond energy. Okay, as we go through and make a bond, we've changed the energy of our electrons. So now the question is, did we make those electrons higher energy or lower energy? Okay, so let's try and draw up a picture here. We've got energy. I'm going to say my atoms on their own are here. So this is the free atoms. Some random energy level. I don't care to quantify it. What I'm concerned about is its relationship to the bonds. So now I move to the bonded atoms, or our molecule. Where would I expect to draw the energy for my molecule with respect to the atoms? Kind of a challenging question. What did we say all of our molecules try and do? They try and go to higher energy or lower energy? Are all you standing at the desks, or are you sitting down? You're sitting down. Why? It's more comfortable. It feels good. If you had to stand the whole time, you expend a lot of energy. We could throw that out there, you know. If you wanted to lose weight, one of the things you could do at work is always stand. You stand at your desk because it expends energy. It takes more energy to be at that higher state. So what are you doing here? You're trying to spend all of your energy thinking about what I'm saying, theoretically. Okay? So you sit instead of stand. So what we're trying to do in nature is achieve a lower energy. So where would we expect to put the energy of that molecule? At a lower energy. Right? Does it make sense to put it at a lower energy? If it was at a higher energy, would my atoms ever form a molecule? No. Like, why the heck do I want to spend all that energy to move up to a higher energy state? It doesn't make sense. Okay? So when we're looking at making a bond, we're looking at dropping the energy. Okay? When we're talking about bond energy, that bond energy is in reference to the gap in energy between our atoms and our molecules. Okay? So everything we're talking about as far as bond energy goes back to that. Okay? I will tell you honestly, I don't have the next set of information memorized. All I've got memorized is this figure. Everything else falls off of this. Okay? It makes sense for me to drop in energy as I make a bond, because otherwise, why would I do it? Okay? So when we look at our energy, when we take a hydrogen atom and a chlorine atom and we put them near each other to make HCl, we're going to release energy because we're dropping in an energy state. We can't create or destroy matter or energy. Okay, so if I drop in energy, that energy has to be released somehow. Most reactions will release it as heat. There are other forms it could be released as? Light is a good possibility. So yeah, there's a lot of different ways we could release that energy. Heat just happens to be the most common one. So if we now want to quantify or put it into an equation, we can go through and show heat as a product because it's being released from the reaction. What if we turn the reaction around? Okay. What's going to happen if we try to break that bond? So now what we're saying is we take HCl and I want to split it into my hydrogen and my chlorine. Where should the heat show up now? Well, where did the heat show up in the previous equation? Where did the heat term show up? Okay, we could say it showed up in the product. So does that mean I should write it in the product here? No. Just like when we were doing our conversion factors, I said, okay, where do you put your numbers? Okay, you put your numbers based on where they showed up next to. Where did our heat term show up next to? HCl. HCl. Where should the heat term show up if I reverse the equation? Next to the HCl. What does this now mean? So heat is a reactant. Okay? It's needed to break that bond. Okay? If heat's a reactant, how could we describe that? Up here we could say heat was released. What's happening in our other equation? Heat is absorbed or added to the reaction. Okay? I know it's kind of a tricky concept, but that's kind of what we're looking at within each of these. So the questions that can be asked is going back to, okay, is heat added or released? Okay. Added and released isn't very scientific, and we know scientists, we like to make up fancy words. Okay. Those of you in the lab on Tuesday, what were those fancy words? Exothermic and endothermic. Exo means out, released. So which of these two reactions is best described as exo? The top one. We have an exothermic reaction. The heat was released. Endo means absorbed. So our bottom equation is endothermic because it absorbed that heat. Okay? And we got a bunch of extra words to throw in here. I just went through and talked through all that. Okay? But I needed the space. So, questions about that? Last sentence is kind of an interesting one. Let's look at our first equation. I'm going to quantify that heat term. That heat, when I go through to make HCl, is now 5 kilojoules. Do you know what a kilojoule is? 1,000 joules. Could convert it to joules. Okay? We don't need to know what a kilojoule is. All I'm telling you is that that is a heat value, is 5 kilojoules. So we don't need to worry about what the unit is. Don't stress about that. Just that that is a heat unit. If we now go down to the second equation, what's the number I should put in for that heat term? 5 kilojoules. It's going to be the exact same number. It's just going to show up on the opposite side of the equation. So our heat can be used strictly as a reactant or a product, just like our hydrogen atom and our chlorine atom, or our HCl molecule. All right, so we get the exact same amount of energy. We're just putting it on a different side of the equation. All right. Next thing I'll throw in there. This again goes, Tuesday lab will have a little bit of a cheat here. What's the change in heat for that first reaction? Okay. I'll write 5 kilojoules, but I'm not quite satisfied with that.
Negative.
Shh. What's the change in heat for the bottom one? 5 kilojoules. Uh-oh, we now have a problem. We're saying the change in energy for both these reactions was 5 kilojoules. But in one case, that energy was released. One case, that energy was absorbed. Those are doing entirely different things. Would we expect the change in heat to be the same? No. There's something that we're missing. That delta symbol means change. All delta symbols in the process of meaning change mean the final state minus the initial state. What's our final state for our top equation? Was 5 kilojoules. What was our initial? If we're not given anything, we can assume that's 0. Final minus initial? We could get a positive value. Interesting. Oh, I know why. Shit, never mind. Ignore that. We got to look at something else for that. Crap. Really didn't want to get that far into it. We'd have to look at the final and initial energies for each of these species. The loss, or the difference in between, is going to be that 5 kilojoules. That's the issue I just ran into. I don't have those numbers, and I don't want to make them up. When we're looking at an exothermic reaction, we're looking at a loss of energy. What mathematical symbol best represents a loss of energy?
Negative.
Negative. So in our exothermic reaction, our change in heat is negative. The energy was released. Our energy is on the product side. If we take a look at the other one, our heat was absorbed. Okay, what's the mathematical symbol best represented by absorbed? Positive. what happens in thermodynamics. You got to be really careful with those signs. Okay? So if I wanted to look at just the change in energy for that first reaction, I would specify it as a negative 5 kilojoules. Because that energy term, that heat term, showed up where? On the product side of the reaction. That negative just means put that energy term on the product side. What does the positive term mean? You need to put it on the reactant side of the equation. Okay? Big lessons on this. Exothermic means heat released. Endothermic means heat absorbed. Focus on that aspect. The signs will become more important when you deal with actual calculations, if you have to, in 151. Okay? Are all bonds the same? So if I take a look at NaCl, what type of bond is that? Ionic. If I take a look at HH, what type of bond is that? Covalent. If I take a look at HCl, what type of bond is that? That's also covalent. Okay, next question, let's switch this around. Hydrogen gas and HCl. Okay, HCl, if I put an aqueous next to that, what does that mean? Acid. Okay, so new question. Hydrogen gas, I'm going to take some of that and I'm going to throw it at you. Okay, HCl, I'm going to take some of that and I'm going to throw it at you. Yeah, shaking heads is a good idea. You're going to be a little bit irritated about one of those if you survived. Okay. HCl is an acid. What happens when an acid hits you? It burns you. You're very unhappy about that. The HH gas does what? Just washes over you and cools you down. Okay? Not going to do much to you. Is there a difference in the nature of those chemicals? Yeah, absolutely. What is that difference due to? The nature of the bond connecting those atoms. Well, if there's a difference in nature of the bond, shouldn't we call it something else? And it turns out, yes, we do. So we end up with 3 categories for types of bonds. Ionic, polar covalent, and nonpolar covalent. So what ends up happening is we subcategorize the covalent bond to explain a large difference in reactivity for some covalent bonds. Okay? So how do we go through and decide which one's which? You'll notice next to the ionic and the nonpolar covalent, I've put in those greater than, less than signs. Where did those numbers come from? Yep. What we're looking at for those numbers is the difference in electronegativity. If your difference in electronegativity, man, that's a big word, electroneg, is greater than 1.7, it's an ionic bond. If it is less than 0.5, it's a nonpolar covalent bond. Well, how do we know if it's a polar covalent bond? It's between those two values. Okay, so if I give you HCl, how can you tell me that's a polar covalent bond? What do you need to do? Find the electronegativities. Okay, we asked this question already. How many of you memorized the electronegativities? Ooh, ouch. We need a better definition for these to be able to determine them so we can quickly look at a molecule and say it's that type of bond. Because we want to be able to really quickly look at a structure and say, I don't want that on me. Okay? So how can we go through and do that? Well, what else did we say was an ionic bond? There it was. Be a little more confident in your answer there. Metal and a nonmetal. That is very characteristically going to push your ionic bond way into a separate category. Okay, so we do have a clear difference there. What's the issue when we move to the covalent structures? As nonmetal and nonmetal, we don't have a clear difference. Okay? We've added these extra terms, polar and nonpolar. What does that mean? Do you know anything that is polar? A magnet. What else is polar? The Earth is polar. What does that mean? We have a north and a south end. Molecules have something very similar. What's their north and south end? For instance, an ionic bond is wickedly polar. It is so polar we call it an ionic bond. What's the characteristic of an ionic bond? Charge. The sodium and sodium chloride is what charge? Positive. The chlorine atom is negative. Right? So when we look at a polar covalent and a nonpolar covalent, let's push that logic a little bit further. In a nonpolar covalent, what partial charges or what kind of charge would we expect to build on either of the atoms? As a hint, we said it's not polar. We want them to have the exact same charge. Okay? If we have a negative, though, what happens when we put a negative near it? It repels. So maybe it's positive, positive. What happens? Repels. Maybe the charge is nothing. Right? So there's a complete equal sharing of electrons, which means neither atom picks up a positive charge, neither atom picks up a negative charge. When is that going to happen? We could look at noble gases, except noble gases don't form bonds. Remember, they're noble, they're inert, they don't want to deal with anybody. When the atoms are the same, when we look at a hydrogen bond to a hydrogen, what's the difference in electronegativity? Nothing, because they're the same atom. They have the same electronegativity. What would I expect for a nitrogen-nitrogen bond? Same thing, nonpolar covalent. Let's look at the most electronegative element on the periodic table, which is fluorine. Let's bond fluorine to fluorine. They're wickedly electronegative. That's got to build a charge. Does it? Nope. The electronegativity is completely canceled. So in a nonpolar covalent situation, what we're looking at is bonding an atom to its exact same type. All right? So no difference between the atoms. So it's same atom to same atom. Okay? You'll notice that that is a very, very narrow definition. For the sake of organic chemistry, we open that definition up just a little bit. We open that definition to include one type of bond. Anybody know what that type of bond is? You may not, that's fine. You haven't taken organic chemistry. Carbon to hydrogen. So if you're looking for a nonpolar covalent bond, you can pull up all the electronegativities, okay, and do the exact calculation. And you'll find that there are some that fall outside of this definition. Okay, for instance, if we bond phosphorus to sulfur, that might very well fall in a nonpolar covalent bond, even though that's not the same atom to the same atom. So this kind of rule of thumb doesn't nail it down perfectly, but it nails it down 90% of the time, you'll see. So when you do homework questions, you should be looking at the electronegativities. When you do exam questions, do you have a table of the electronegativities? No. So what should you be assuming for a nonpolar covalent bond? Same atom to same atom and carbon to hydrogen. Okay, so we've got a definition now for our ionic bonds, and we have a definition for our nonpolar covalent bonds. How do we figure out our polar covalent? That's a nice simple answer. Everything else that didn't fit in that section. Okay? Because, and we've announced this multiple times, I'm an organic fan. When we look at organic chemistry, we have metals and nonmetals for our ionic, we have carbon and hydrogen for our nonpolar covalent, and everything else is really narrowed down to oxygen, nitrogen, and your halogens. So if I bond anything to one of those 6 elements, I have a polar covalent bond. Okay? Questions about that? So all we're trying to do is nail down specifically what types of bonds there are. You are primarily concerned about ionic and covalent as your main categories. We will talk about polar covalent every so often. We'll talk about nonpolar covalent every so often. Okay? Questions about that? Okay. Lewis structures. This is the one that really does throw people for a loop. Okay? When we're trying to go through and describe these structures, we've talked about atoms and what the atomic structure is, but now we're starting to make molecules. When we put molecules together, we can come up with some general idea on what's going to interact between them. And we've talked about this. We bring two atoms near each other, what's the first thing that interacts? The electrons. Which electrons? The valence electrons. Which electrons don't interact? Non-valence, reasonable answer. Okay, we do come up with a term for it. Those electrons are the ones in the very middle of our structure. Those are known as the core electrons. Okay, so you may see that term float out there. Okay, so Lewis came along, I believe early 1900, and was trying to come up with an explanation for how these molecules can interact. And we know we're looking at these valence electrons interacting with each other, and he wanted to be able to predict the types of bonding available to each of our atoms. So how could he go through and do this? So the first thing he did, you'll notice as we look at a couple examples up top, is do what? Where are all of those elements located on the periodic table? Where? The first two rows. Why did he not start looking at how silver interacts? Or how, say, maybe barium interacts? It's so big, it's going to change the complexity of the question that he's trying to answer. So he simplified it down and looked at some very basic structures and said, okay, I know these molecules exist. I want to try and explain how they can exist. Okay? When we look at those first two rows, what orbitals are we concerned about? Only the S and P. Again, why? Simplify the argument as much as possible. We could simplify it all the way down to just looking at the s orbitals. We could just look at the HH bond. The issue with that is, yeah, that's great to explain the HH bond, but could I apply that to anything else? No, I've lost pretty much all ability to apply that information. So what we want to do is take a step above that complexity and move up into S and P orbitals and see how those can interact, where we have more elements to work with. Okay? So we're looking at the highest energy orbital for each of these. And we're going to be concerned about the valence electrons. When we look at that second row, how many electrons could possibly be there? For our valence electrons, second row, maximum number of electrons. 8. Okay, so we said 8 electrons. I'm a geometric whiz. What structure has 8 points? Okay, octagon's not a bad idea for a two-dimensional object. Are all of our atoms in 2 dimensions? No, they're 3 dimensions. So what 3-dimensional object has 8 points? A cube. So he said, okay, I'm going to say all of my molecules are cubes. And at each of those points is where I can put a valence electron. Okay? So let's cross one of those things out for the moment. Let's cross this guy out. Let's look at the bonding between 2 hydrogen atoms. So we've got 1s1 for one of our hydrogens, and the other one would be also 1s1. So my hydrogen nucleus is floating somewhere in the middle of that cube. Okay? And if I want to look at these structures, I could go through and say, oh, this corner has an electron on it. Where do you think he put the electron from the other hydrogen atom?
The opposite corner.
What do you mean by opposite corner?
The bottom left.
Bottom left. That's bottom left, right? That's what you're talking about. What happens as I bring those 2 atoms near each other? what happens to the line? I can now intersect those lines, and I bring those close. One hydrogen can fill that empty space with its electron, and the other electron can fill that empty space. And what we now have is a bond between these cubes. Kind of neat. All right, so let's scale this up to HF. HF, when we look at our electron configurations, our hydrogen is again a 1s1. And our fluorine atom has what electron configuration? 1s what? 1s2, 2s2, 2p5. Of those electrons, which ones am I concerned about? Everything in the second energy level, which is the 2s2 and the 2p5 for our fluorine. Those are our valence for our fluorine. How many electrons do I need to put into my cube? 7. Does it strictly matter where? Not really. But for the sake of actually getting this to overlap somewhat interestingly, we want to go through and do it this way. And we'll put in our 1 electron for our hydrogen. What happens now? Hydrogen can share its 1 electron across, and the fluorine can share, its 1 electron across. The net result is I have how many bonds? 1 bond. I've now shared 2 electrons, I've made 1 bond. Okay. Cubes. How many of you drew out the cube just now? Oh, I'm sorry. I didn't mean to make you actually draw that out. Should have announced that. Really difficult to draw out the cubes, right? Particularly if we moved up to something like CH4. Now instead of 1 bond, we're going to have 4 bonds. That's a lot more difficult to deal with. Okay? So instead of working with cubes, is there a 2-dimensional shape that could still maintain this overall impression? What's that 2-dimensional shape? That still gives us this idea of the sides of a cube. Square. Take the square, flatten it out. So if we look at our hydrogen atom again, our 1s1, we can draw our hydrogen atom in the middle, okay, or draw it, and we want to specify that 1 electron it has. Okay? It's in the middle of a box, right? We want to put that 1 electron around it. So there's that 1 electron. You'll notice where I'm going to put it is on one of the faces of my square. And that's because when we made the bond in our cube, we put it on a face. It was the sharing of electrons on one face. Okay? If we go through and look at our fluorine atom, okay, we said it was what? 2s2, that's a sloppy 2. What letter? P. 5. When we go through and we look at our fluorine atom, we'll put its box around it, and we now want to put all of those electrons in. How many electrons do I need to put in? 7 valence electrons. So I'm going to start putting those electrons around the fluorine. Does it matter where I start? No, because these are 3-dimensional objects that freely rotate and move at any given point. Okay? So I'm going to go through and start at the top. I'm going to put 1 electron there. Where should I put the next electron? When we fill orbitals, how do we fill them? Singly first, all at the same energy, then we go back and double. So when we're dealing with our Lewis structures, I'm going to fill each of those faces singly first. And now I've got only 4 electrons there. I need to put in 7. Now I can go back through and double. Now I've got all 7 electrons around my fluorine. Now when I bring my fluorine near my hydrogen, what happens? Hydrogen's electron sees fluorine. Fluorine's electron sees hydrogen. And what happens? We've now created a bond. Okay, so now let me erase those arrows a little bit. To create that bond, we had how many electrons? 2. So we could just say, well, there's 2 electrons between atoms and leave it at that. Except now every time you go through and draw a Lewis structure, you're going to have a bunch of dots. Okay? Are all those dots the same? Okay? Meaning, is this pair of electrons have the same characteristics as the pair of electrons between the hydrogen and the fluorine?
No.
No. In one case, the pair of electrons is not bonding, and in the other case, it's bonding. Is there a difference between not bonding and bonding? Yeah. So it's a good idea if we come up with some kind of notation to specify that difference. What do we end up turning that bonding pair of electrons into? A line connecting those atoms. We now have a bond connecting hydrogen and fluorine. Okay? Simple as that. Questions about that? Okay, I'm going to guess you want another example. Okay, so let's try another example. Let's look at CH4. So we'll erase everything. I'm looking at our CH4, and I want to determine how to put this structure together. One of the very first important steps to go through and do is to know how many electrons need to show up in my structure. So I can look at the electron configuration for carbon, which is 1s2, 2s, 2, 2p, 2. Of those, which ones am I concerned about? Which means carbon's going to bring in how many electrons? What's the electron configuration for hydrogen? 1s1. What's its valence electrons? 1. So it brings in 1 electron. So I need 5 electrons in my structure. Everyone agree? There's 4 hydrogens. Each one of those hydrogens brings in 1 electron, which means what I'm looking at here is not 5 total electrons, but 8 electrons. 8 electrons need to make it into my structure. Okay. Next step of this is trying to put our atoms in. Okay. Well, with HF, it was kind of pseudo-obvious. We just put the 2 atoms. There was only 1 bond. We didn't have to worry about it. So does this make sense? Okay. Really, with no rules, we have no idea. Okay. When it comes to Lewis structures, and what you're going to go through and work out is we want to pick a center atom. All of your structures will have a center atom. What is that center atom going to be in this case? What is the difference between carbon and hydrogen? True, but we could go through and change that to nitrogen. Nitrogen has 5 valence, so that doesn't explain why carbon with 4 should be the center, and nitrogen in the next case is the center. I remember there was that all-important term, and I said everybody needs to know because it explains so much stuff. Electronegativity. Which is more electronegative, carbon or hydrogen? Carbon. Our center atom is the least electronegative that can still bridge. Okay, what do I mean by bridge? Hydrogen can only form 1 bond because it only has 1 electron. So it can't bridge atoms. So carbon will be our center atom. Okay. What do we do with all the hydrogens?
Put them in a circle around carbon.
Okay, so I can go through and do this. That's one possibility. Where did our Lewis structure start? Around what shape? Okay. Started with a cube that we converted into a square. So when we draw out our Lewis structures, remember that square. You don't have to draw the square, but remember it's there. Now what we'll do is put our hydrogens on each of those faces. Next part, we need to get our electrons into the structure. How many electrons do we have to put in? 8 electrons. Where should I start putting them first?
Carbon.
Why carbon?
Because it's the center.
Okay. This is how most tutors will explain it. Put it around your center atom. I call crap. Politely. Okay. Don't put them around the center atom. Put them around the most electronegative atom. Why? What did electronegativity measure? The ability to hold bonding electrons. So I want to make sure that those electrons go to the atoms that want those electrons the most first. In this case, which one's the most electronegative? Carbon, which happens to be the center atom, but not always. Okay? So I'll start putting my electrons individually around. 1, 2, 3, 4. But carbon only brings in 4. Should I stop? No, why not? I need to put in 8 total electrons. So I'm going to continue to put in those 8 total electrons until I have completely satisfied my most electronegative element. My most electronegative element here is carbon. Carbon now has its 4 sides completely saturated with electrons. I cannot put any more electrons around that carbon, okay, because we've got only those 4 sides to work with. Okay? In that process, how many electrons have I put in? Can I put in any more electrons? No. So I'm done putting in electrons. So now what do I do? Now what we should go through and do is say, are those electrons in bonds? Well, how do we know they're in bonds? The electrons for a bond are located where? Between 2 atoms. So now I go through and look at it. Is this first pair of electrons between 2 atoms? Yeah. How can I make sure that that pair of electrons looks like a bond instead of a pair of electrons? I can turn it into a line, and I'm going to start to erase my square around it. So I now have a line connecting the carbon and the hydrogen. How about the next pair of electrons? Another line. Next pair of electrons. Another line. Next pair of electrons. Another line. What I now have is the Lewis structure for CH4. Okay? Questions?
I do. So if you have 2 atoms for each hydrogen, isn't it double bonding?
We'll deal with double bonding later.
But that's not double.
We don't want to get into double bond yet. Yeah, keep it simple. Okay, that's what my dad liked to call, keep it simple, stupid, whenever he was talking to me. Nice guy. Okay, so it would be nice if we had a list of rules that we could go through and follow, right? Make sure we can keep track of each of our individual steps. Too bad you don't get any rules. No. Nice, big, massive list of rules. We just walked through each and every single one of these steps. The first thing we did, we totaled the valence electrons. Okay? We didn't talk about counting charges yet, but we'll look at that. Okay? Choose a central atom. The central atom will be the least electronegative that can bridge. Okay? To bridge, it has to have more than just 1 electron. Okay? And less than 7, actually. Okay? We'll add our electrons in pairs to the most electronegative atom first. Because what we're trying to get up to is 8 electrons around our central atom. Why do we want 8 electrons? We looked at our first and second energy levels. The total electrons in our second energy level? 8. Why 8 electrons? We fully saturated our second energy level. Okay? Why did we not get 8 electrons around hydrogen? Because it doesn't fit into the octet rule. So this is our octet rule of 8 electrons around our center atom. If we look at hydrogen, how many electrons can hydrogen fit? Look at its energy level. Only 2 electrons. So hydrogen is an exception to the octet rule. Okay? Because it only wants 2 electrons around it. There are 2 more exceptions to the octet rule. Boron and aluminum. They are happy at 6. Okay? And we'll look at the reverse exception going more than an octet a little bit later. Okay? We'll continue to add electrons around the rest of the atoms until we have accounted for the total electrons. Okay? You cannot exceed the total, regardless of what you think each atom needs. Okay? You can't add more electrons than you started with. Okay? Where we get with the double bond is actually rule 5. Okay? If we have an atom that has not achieved its octet, what we can go through and do, actually that's not rule 5, not rule 6. Rule 5 is convert any pair of electrons in between atoms into a line to represent that bond. Rule 6, if we have any atoms that have not satisfied their octet, then we need to move electrons into a bond, okay, to satisfy that octet. That's where we get double bonds. Okay? That is probably one of my biggest peeves, because when you look at how tutors will go through and do this most typically, okay, they'll say, oh, that has a double bond, just make it a double bond. How the F did they know it was a double bond? They already did the problem. That's cheating. Okay? They need to come up with a reason why it's a double bond. It comes back to following how you put electrons into the structure. If you put the electrons in the fashion that I am telling you to put them in, double bonds will naturally fall out. You'll see them when they need to show up. If you put them in any other fashion, it won't be obvious, and you're going to keep getting frustrated trying to find where to put an extra pair of electrons. Put it in this fashion, you should be set. Resonance really falls naturally out of rule number 6. Okay? If there's more than one place to put electrons in, that means we have multiple structures. Those multiple structures are referred to as resonance. The last thing is rule number 7. Organic chemistry students still struggle with assigning formal charges. You guys thankfully don't have to stress too much about it, because you don't have to assign it to an atom. You just assign it to the molecule. And when we look at examples, you'll see that. Okay? So, to absolutely ensure that everybody is actually doing this, we're going to put this down as a quiz. And by a quiz, don't stress. I'm not actually going to grade it. I'm just pretty much going to look to see that you wrote something down, that you attempted to do these. Okay? So don't stress on it. Feel free to raise your hand, ask questions, talk to other students around you. I want you to get this figured out. We aren't being concerned about getting it right or wrong. See how long it takes to do each one. So we'll start with CF4. Okay, and I don't want to really call people out too much on this, but I am going to do it. I noticed a lot of people, as I walked around, wrote their name on it, and then wrote number 1, and then wrote CF4, and then drew this. Not technically wrong, but you aren't following the steps that I've outlined. I've outlined the steps for a very, very good reason. It helps you find the resonance, which is the hardest aspect of this. Okay? This question or this problem doesn't have resonance, so it's not a big deal. Okay? You get the answer, and that's the issue, is every time you can get to the answer, it's the amount of effort and thought that you have to work through to get to the answer. If you follow the steps, I've minimized thought. Okay? You do have to know the steps, but I've minimized the thought. Okay? So let's try this again from how I've suggested doing this. So we'll still stick with CF4. First rule is to do what? Total valence electrons. Okay? You should start being able to look at an individual atom and say that atom has this many valence. You don't need to write out the electron configurations. So I'm not going to write it out this time. How many valence electrons does carbon bring in? 4 valence. How many electrons does fluorine bring in? How many fluorines are there? So my total valence is 32 electrons. Okay, I cannot change that number. Okay, that's where my step 1 comes in. The central atom is going to be the least electronegative that can bridge, and that's where we ran into the issue with the CH4. Hydrogen is lower in electronegativity, but it can't bridge. It can't connect multiple atoms. Okay, so in this case, our center atom is going to be carbon as the least electronegative. So if you know your electronegativity trends, you can figure that out. Where do we then put the fluorines? Okay, on each face of our square that's invisible now around the carbon. Okay. Again, I saw people jumping steps. No! That's not the next step. What's the next step? Okay. We don't even need to box the carbon. According to our rules, it's rule number 3 now. Add electrons where? Which atom is the most electronegative? Which atom is the most electronegative? Fluorine is the most electronegative. Okay, and this is where my path diverts a lot from what the textbook goes through and explains. That's because my path gets you to resonance. The textbook gets you off into some weird back alley somewhere that you don't want to be. Okay, so we'll start putting them around fluorine first. Does it matter which fluorine? Why not? They're all the same. So we go through and we put on 8 electrons around each fluorine. Why 8? It's our octet rule. Continue putting our 8 electrons around fluorine. How many electrons have I put in now? 32. What does that mean? Stop putting in electrons. Can't put in any more. We move to the next step. Continue adding to reach the total electrons. Well, we've reached the total electrons, so we can't continue to add anymore. Now what we'll do is move to step 5, which is convert pairs of electrons that are located between atoms. So this is the abbreviated rule that I've got up here. So between atoms, we'll convert into a line. Where do I have electrons between atoms? Each of the fluorines and the carbon. Holy crap, that looks like the exact first thing that we drew up to begin with. It's because it does. Okay? You do get to the same answer. It's just a question of how you get there. James, you had a question.
Yeah, you had 2 or 8 electrons attached to each of the fluorines.
Each of the fluorines, yep.
How come you don't do 1 on the inside of each of the fluorines and 1 on the inside of carbon?
So I'm not putting electrons around carbon. I put the electrons around the most electronegative every single time. I don't touch carbon because it's not the most electronegative. So I start with fluorine. Oh, that's my most electronegative. 8 electrons around. 8 electrons around. 8 electrons around. Okay. When we then look at it, we have a pair of electrons between atoms. Both the fluorine and the carbon had a pair of electrons sitting there. We turn that into a line. That gives us the bond. Do you have a question?
So you do, but in so the answer is that you still have to have the electrons around the fluorine. You can't.
You still have to have the electrons around the fluorine, which is where a lot of people will miss. When we're looking at Lewis structures, we're trying to explain where the valence electrons exist. Fluorine has all of those electrons around it. If you don't specify those, your answer is wrong, because the whole point is to specify where all the electrons are.
And those aren't bonds, so you can't do.
And those are not bonds. Okay. So then that's the next question. You'll notice old school chemists, or at least I think it's old school chemists, will convert every pair of electrons into a line. I really don't like that idea. I won't mark you wrong for it as long as you don't make it look horribly wrong. Okay. When do we use a line? As a bond. If I start going through and converting every pair of electrons into a line, it can get very confusing. Okay, yes, it abbreviates the notation, but to me it gets a lot more confusing. So what I do is leave them as the pairs of electrons.
Okay, so you couldn't put because it's not a bond between.
Because we aren't showing the bonds between, there are no bonds between the fluorine atoms.
And
Yeah.
the carbon one, so just the one line can go there. Not
Just the
4
one line.
lines.
Yep. Okay, so we can only put those 2 electrons on a face unless we hit that satisfying octet rules being an issue, and we can get to that later. I'm going to real quickly whip through the NH4. So NH4 plus, electrons nitrogen brings in is 5. Hydrogen brings in 1, but there's 4 of them. What does that positive charge mean?
Loss of electrons.
There's an imbalance of the electrons and the protons. Since I can't change the protons, I can only change the electrons. How can I make this structure positive? I need to remove an electron. 9 minus 1? 8 electrons. My center atom is the least electronegative that can bridge. Hydrogen can't bridge, so we drop in the nitrogen, and we'll now put in my hydrogens. Does it matter where I put the hydrogens? No. Why not? Okay, let's call it out. Back corner, since you guys are talking, I'll call you out. What's my name? Mike. Andrea. Andrea, where are you? Yeah. What's my name? Wait, it's the same name?
Yes.
Why? You were looking at my back, she was looking at my front. Same person. Okay? Molecules, same issue. What we're drawing is a two-dimensional drawing of a three-dimensional object. That molecule can spin, flip, rotate, turn over on its head. All of those are options. It doesn't matter where I put the hydrogens around it. Okay? Now I can go through and put in my electrons. How many electrons do I put in?
Why do you only have 3 hydrogens?
Oh, sorry. My bad. NH4. Okay. Now I want to put in my electrons. Where do I put my electrons first?
Hydrogen.
What were you saying? Which atom's the most electronegative? Nitrogen, which turns out to be the center atom in this case. Okay? So we'll start putting the electrons around the nitrogen. How many electrons have I put in? 8, which means I've added all the electrons I can. I can now convert them into bonds. And I know I'm doing this really fast now. We now go through, verify that we have our octets. Yes. We don't have to worry about resonance. Our formal charge, we can go through and say that that overall structure is positively charged. We can put a big old bracket around the whole thing saying that whole structure is positively charged. You now have that one. I will draw on Tuesday OH minus and SO3. We'll probably move into shape as well. Oh, please turn in your quiz before you leave. And we are done.